Hello, dear students. Today's topic is probability in the undergraduate level. So let us first discuss about some concept of random variable, and after that we'll move through the distribution functions. So in describing the sample space of an experiment, we did not specify that an individual outcomes needs to be a number. Suppose the sample space of tossing two coins is given by this is the sample space for tossing two coins, and which are not real numbers. You see, these are not real numbers, so it will not be easy to develop a mathematical theory dealing with these objects. Now it is possible to establish a correspondence between outcomes of a random experiment and a given set of real numbers by means of a mapping defined on the event space of the given random experiment as domain. So if we define any real valued function, defined on event space of our random experiment is called our random variable or stochastic variable. So let E be the random experiment described by the event space S, and if X is any real valued function on S, that is if X from S to R, look at the mapping X from S to R, then X is called a random variable. So let us illustrate with the mapping concept. So this is S and this is R, real number. So suppose you toss a coin, head, tail. It's a very small example. So this is the mapping. Now suppose head, if we get head, let us define, so this is X, the mapping X. So if we get head, then suppose the real number is 1, and if we get tail, suppose it associated with the real number 0. So head goes to 1 and tail goes to 0. So we can associate with the event space S with the real numbers. So this is the first time we are associating any event with the real number. So this is the mapping. This is called the random variable or stochastic variable. And the range of the function X, that is the set of all values which X takes up, is called the spectrum of the random variable. So in this case, in the above case, 0 and 1 is the spectrum. Spectrum consists of 0 and 1, only 2 points. So accordingly, the spectrum may be discrete or continuous. In this case, you have a discrete set of points. So discrete, we want to say finite or countably infinite, and or continuous. Accordingly, the random variable is said to be discrete or continuous. We have another example to illustrate that. Let E be a random experiment of rolling a die. So S is 1 to 6, and we define X from S to R by x1 equal to 0, x2 is equal to 1, x3 is equal to 0, and so on. So that is, we taking the odd faces to 0 and taking the even faces to 1. So x equal to 0 denotes the event odd face, and x equal to 1 denotes the even face. So the spectrum in this case is 0, 1. Naturally, you have only two real numbers association. So what is the probability of x equal to 0? Probability of x equal to 0 is nothing but getting an odd face. So probability of odd face is 3 by 6, that is half, and probability of even face is x equal to 1, that is x equal to 1, that is 3 by 6 again, then that will be half. So this is the concept of the random variable with some examples. Now let us give an example of a continuous random variable. People will ask about the continuous random variable. If x denotes the lifetime of an electric bulb, then x is a continuous random variable, and its spectrum is the set 0 to infinity. So this is the interval. So any kind of interval is a continuous random variable. So this is an example of a continuous random variable. Next we define probability space. Very important concept in probability. The entire mathematical theory of probability will be built up by three objects: the event space S, the class of events delta. This may be quite difficult to understand for the students. And the probability functions pre from delta to R. That is, delta is your class of events. What is class of events? So there is a short description of that. So class of events, the class delta of subsets of S forming the class of events of a given random experiment. There are three conditions, three properties. S belongs to delta. If A belongs to delta, then A bar also belongs to delta. That is, complementary event is also belong to delta. Delta is the class of subsets of S. If A1, A2, etc. belongs to delta, then summation n equal to 1 to infinity an belongs to delta. So these are the three restrictions actually. Any member of delta will be called an event. The class delta of subsets of S satisfying 1, 2 and 3 stated above is called the sigma algebra or sigma field. So this is the small concept of sigma algebra and sigma field. So this is how we define the class of delta of subsets of S. So here we are mentioning that the class of events delta. Now the ordered three tuple, that is the S delta P. S is the event space S and delta is the class of events delta, and the probability function P from delta to R is called a probability space. That means the three tuple consisting of S delta P is called the probability space. So probability space is nothing but containing these three concepts. So next we define the distribution function. The distribution function of the random variable X with respect to the probability space S delta P is a real valued function fx of a real variable X defined in real line, where fx is given by probability of random variable X between minus infinity and X. So this is the main expression for the distribution function. There are some properties of the distribution function. I am not going to the proofs of those properties. I am just mentioning the important properties. The distribution function fx is monotonic, non-decreasing. That is, if b greater or equal to fa when b greater than a. Number 2, limit x tends to infinity minus infinity fx is equal to 0, and limit x tends to infinity fx is equal to 1. Number 4, fx has a jump discontinuity on the left at x equal to a. So if you draw the diagram, next we will draw the diagram for fx for more understanding. We will see that fx has a jump discontinuity on the left at x equal to a. The distribution function fx is continuous on the right at all points. And lastly, if you need to find out the probability of a less than x less than equal to b, probability of x between a and b, then it is given by fb minus fa. So these are the important properties of distribution function. Let us draw the distribution curve. The curve y equal to fx is called the distribution curve, which is confined between the line y equal to 0 and 1. So this is the diagram of distribution curve, which is confined between y equal to 0 and y equal to 1, because total probability is always 1. Now let us describe discrete distribution. If the random variable x takes up a discrete set of values, these are the discrete set of values, it's countably infinite with probabilities, probability of x equal to xi is equal to fi, I equal to the spectrum points at I equal to 0, plus minus 1, plus minus 2, then the distributions are given by, in xi less than equal to x less than xi plus 1, fx is given by already defined above, and equal to, we can write alpha equal to summation alpha equal to minus infinity, it's a notation, alpha equal to minus infinity to I, that is at that point I, probability of x is equal to x alpha, and already defined probability of x equal to xi is a number, is fi. So alpha is equal to minus infinity to I f alpha. It is given by f alpha according to this. So what we see the conclusion is that fx is a step function having a step of height fi at each point xi of the spectrum. So this is very important. The final conclusion. Let us elaborate it. Let a random variable x take up a discrete set of values x1, x2, xn. With this is the restriction with probabilities, probability of x is equal to xi is equal to fi. Then the distribution function is given by the following. So in minus infinity to x1, fx is given by 0 because x1, before x1 there was no distribution, so it will be 0. In x1 less than equal to x less than x2, fx is given by probability of x equal to x1. Only one point you have, spectrum point, that is x1, so you have f1 only. In x2 less than equal to x less than x3, you have 2 points now because you will start from minus infinity till x2, so you have 2 spectrum points, x equal to x1 and x equal to x2, so you have f1 plus f2, so on. And lastly you have at xn points, so you have the total probability is 1. So now you conclude fx is given by fx is equal to 0 in this, and f1, f2 and finally 1. Let us draw the diagram for that. You look at that, you will start from minus infinity to x1, so this is your you have a 0. At x1 you have f1, at x2 you have f1 plus f2, so the height in this case is this length is f2, this length is f2. Again at x3 you have f1 plus f2 plus f3, so this height at x3 is f4. So we can say fx is a step function having a step of height fi at each point xi of the spectrum. Now we define the concept probability mass function. Let probability of x equal to xi is fi. A function f from r to close interval 0, 1 is defined as fx is equal to fi if x is equal to xi equal to 0 elsewhere. The function f defined above is called the probability mass function of the random variable x. So fi must satisfy the following conditions, actually 2 important conditions, that is if I greater equal to 0 for all I and summation I equal to 1 to infinity fi is equal to 1. That is, this is always true for any kind of distribution. So this is the probability mass function definition and 2 restrictions for possible probability mass function. Now there is an analogy to mechanics by considering a total mass of 1 unit distributed over the real line with the entire mass located at the points x1, x2, etc. So numbers fx is equal to fi represents the amount of mass located at xi. So this is the analogy to mechanics. Next we define continuous distribution. The distribution of a random variable x is said to be continuous if the distribution function fx is continuous and its derivative f dash x is piecewise continuous everywhere. So this is the definition of continuous distribution. Now since we already know that probability of a less than x less than equal to b can be written as fb minus fa, so we can write in integration form integration a to b f dash x dx, and f dash x dx is, suppose f dash x dx is fx. So this is the primitive. So fx is called the probability density function. So new terminology in this case, probability density function. So in continuous we use the term probability density function, in discrete we use the term probability mass function. Making a tends to minus infinity and replacing x by x, we can write the distribution function in continuous case as this. This is the distribution function in continuous case. Now what are the restrictions in this case also? The similar restrictions but in a different form. Fx greater equal to 0 for all x and minus infinity to infinity fx dx is 1. So in that case we have used the summation symbol. In this case, as this is continuous distribution, we are using the integration symbol. So this is, now we'll give you some examples of distribution, that is discrete distribution as well as continuous distribution, satisfying those properties. First, we discuss about binomial distribution. This is a discrete distribution. The spectrum of the binomial NP distribution consists of n plus 1 points, 0, 1 to n, that is xi is equal to I. These are the spectrum points. And the probability mass function, because probability mass function for discrete distribution, so fi is given by probability x equal to xi, probability of x equal to I, and this is the PMF. NCI p to the power I 1 minus p whole to the power n minus I, where p is the probability of success and q is the probability of failure, and q is given by 1 minus p, and p is the only, n and p are the two parameters actually, number of a positive integer, and p is the probability of the binomial distribution, and we will say x follows binomial NP distribution. This is the notation for using that. And we know that this type of problem we can apply binomial distribution to those problems where success, failure, head, tail, 6, no 6. So these are the cases. So we will see later on in the next lecture the how to solve with problems of binomial distribution. Another discrete distribution is Poisson distribution. The spectrum of the Poisson mu distribution is given by fi, probability of x equal to xi, and probability x equal to I is given by e to the power minus mu, mu to the power I by factorial I. So this is the spectrum of the Poisson mu distribution. This is the probability mass function. Is the and mu is the mu greater than the positive is the only parameter of the Poisson mu distribution, and x follows Poisson mu distribution. Let us give some examples of continuous distribution, uniform distribution. First is uniform distribution. This is a continuous distribution. The density function, in this case we use the term density function. The density function is given by fx is equal to 0, minus infinity to a, and b to infinity, and 1 by b minus a in the range a to b. So this is the diagram. In this range it is 0, also in this range it is 0, but a to b it is given by a value 1 by b minus a. So this is the uniform distribution, and a and b are the only two parameters of the distribution. Very important distribution of continuous is normal distribution. Is very important and a very too much applications in the real world. We'll see later. It is normal distribution is widely used by so many people in so many branches. So the density function is given by normal, we say this is normal m sigma distribution is given by fx is equal to, the density function is given by fx is equal to 1 by root over 2 pi into sigma e to the power minus x minus m whole square by 2 sigma square, and the range is minus in the whole real line. So this is the density function. It's quite complicated expression, but it's sigma is the actually the standard deviation of the distribution, and m is the mean of the distribution. This sigma is the standard deviation and m is the mean of the distribution. So sigma square is the variance. So m sigma are the only two parameters of the distribution. M sigma are the only two parameters of the normal m sigma distribution. So x is a if we substitute m equal to 0 and sigma is equal to 1, so this normal distribution transform into standard normal distribution. In this case the density function is given by this. This is actually standard normal variate. X is standard normal variate in this case. So this is the density standard normal density function, and the curve of the standard normal density is bell shaped. This is the bell shaped and symmetric about vertical axis, and 50% we can say the total area under the curve is 1, 50% data this side and 50% data this side. So this is the very important distribution, and so we talked about two discrete distribution and two normal distribution. Thank you.